we're asked to find the number of diagonals in a selection of polygons. This question starts off tame, with hexagons and octagons, but ends up with icosagons, which are 20-sided shapes, and even the general case of an n-sided shape. So let's get started. We're given the examples of quadrilaterals and pentagons, and with these simple shapes we can simply count the number of diagonals from the diagram. But already you can imagine that at octagons it's not fun to draw an 8-sided shape and count by hand all its diagonals. So we better come up with some general idea that helps us to simply look at the number of sides and calculate the number of diagonals without drawing it. As a simple example, so we get the idea, let's use this hexagon. Let's try to approach this problem systematically and just count the diagonals by hand. Start with this vertex. Clearly 3 diagonals can be drawn that come out of this vertex. Moving on, 3 more from this one. But by the time we get to this 3rd vertex, 1 has already been drawn, so we can only add 2. I'm going to start labeling these vertices with how many diagonals came out of them. 3 here, but only 2 here. And already at the 4th vertex there's only 1 diagonal that remains to be drawn. You see at the next one, and the next one after that, the maximum of 3 has already been drawn. So 3 plus 3 plus 2 plus 1 gives us the 9, which is the answer to this question. Now, if you're already thinking about generalizing, you might think, aha, there's a pattern here, 3, 3, 2, 1, maybe I can do the same for a heptagon, an octagon, and figure out what pattern it is. Unfortunately, that's quite hard to do. There is a better way, and it's called overcounting. And I'm going to stress that this will come up again and again in these geometric counting problems. So you should become familiar with it. Let me show you. When you first looked at this, you might have thought, before we got to the 3rd vertex, you might have thought, well, this shape is symmetrical. So it's just 3 diagonals out of each vertex. There's 3 diagonals out of each vertex, and there are 6 vertices. 3 times 6, 18. Something like that, okay? But quickly you realize the problem of overcounting. At this point, we already have this one drawn. But what if I told you that this problem of overcounting can be a very useful problem to have? I will simply ignore that this diagonal has been drawn and draw over it. Oh, that one didn't belong there. That's only the first one. Second one. Right, this one has already been drawn. And so has this one. First one there. Double line, double line, double line, and double line, double line, double line. So I've gone around all 6 vertices and drawn 3 lines out of each. There are currently 18 lines in this drawing. But we can see that it's not that we have a random collection of lines. We have 2 lines for every diagonal. Exactly 2 for every single one. So we can simply divide this 18 by 2 to get the answer, which is 9. Now, this method is generalizable, unlike the other one, where you simply count by hand without overcounting. So you overcount and then divide by 2. You allow yourself to go over the limit, and then you adjust. This idea is everywhere. So please get used to it if you want to do these advanced counting problems at 11 plus. How does this help us with the octagon? We don't need to draw the octagon anymore. We know that a certain number of lines will be drawn out of each of 8 vertices. Let's just figure out quickly how many. Okay, look at this pentagon, for example. If I start at this vertex, only these 2 lines that I can draw to other vertices count as diagonals. Why? Because I can't go from this vertex to itself, that's not a diagonal. I can't go to that vertex because that's already a side of the shape, and I can't go to the other one either. So for each vertex, 3 vertices are excluded, right, from the total number of vertices. Only the total number of vertices minus 3 will give me diagonals of the shape. So with an octagon, I start with 8 vertices in total. I multiply it by 8 minus 3. Right? This is the number of vertices. This is the number of lines that will come out of each vertex. And then I divide this number by 2. This is 8 divided by 2, which is 4, times 5. So the answer is 20. So we have 9 here, we have 20 here, and this calculation here should give you a hint of what the general formula is. It is n, the number of sides of a shape, multiplied by n minus 3, divided by 2. And this formula should go in this row down here. Let's now work out the 2 remaining rows. If there are 3 sides in a polygon, that polygon is a triangle. So we don't even need the formula for this. There are 0 diagonals in a triangle. Although, you should confirm with the formula, and it works, right? n minus 3, in this case, would be 3 minus 3, which is 0. So the whole thing is 0. For 20, it is 20 times 17 divided by 2. 20 divided by 2 is 10. 10 times 17 is 170. And that's how this question is done.